So the plan for today is to leverage all of the things that we learned with our LSTM over the last week or so and adjust some of the parameters. I want to see what we can get from a loss reduction perspective. Can we make it better? Our dictionary, we got our tags. We build these up with a mask that we set at 0. So that way we have something that we can ignore, right? So because it's random data. We don't know what's going to be in the data. We don't know what the length is. It's the same thing for these large language models and transformers as well. We're using LSTM, which is a precursor to the transformer. Pytorch application. We built an LSTM model right here. Really simple. If you look on the screen, there's not much to it. In fact, what is that? There's only 19 lines of code, right? 19 lines of code. For the model, the rest of it is all data manipulation. And there's 150 lines of code in here. This is our LSTM right here. We got it to work really well. We thought we were being clever with our unsqueeze. And in fact, I do want to try, all right, so this is going to be a to-do item here. So we'll do this today. And then we're going to mess around with this because I want to see what the difference between view is with one negative one and an unsqueeze one, because I thought they looked identical, but apparently they're not. I need to see what the difference is. I need to see the difference. Steve, implementing the LSTM part of the speech tagger with character level features. Oh, wait, I want to read through this. Let's read through this. Let's read through this really quick. In the example above, each of the words had an embedding, which served as the inputs to our sequential model. Let's augment the word embeddings with a representation derived from the characters of the word. And now we're into something weird now. I thought we were just doing words, but apparently we can do the characters as well. What does the embedding even look like at a character level? Because now the tokens are 1 through 26, right? Or whatever your alphabet length is. You casually read through the RP. We expect that this should help significantly since character level information like affixes have a large bearing on part of speech. Sure, they mean more if you put them together in words. For example, words have affix-ly are always almost tagged as adverbs in English. Oh, the ly. Oh, interesting. Okay. So if we were going to create a tokenizer, we want to take the root word and separate it from, what do you call it? Affixes, prefixes and postfixes, right? Or suffixes. That would give more meaning and intent. So if we need a better word tokenizer is what we need. I'm curious about, so character level information, like suffixes and postfixes, right? That can add some additional detail into the meaning as it's being represented in the text that we're putting into the model. We're gonna learn what we built. So we spent a lot of time building the LSTM, the long short-term memory model, right? Long short-term memory model, LSTM, right here. We're going to look at everything that we wrote. We're gonna review all the code, kind of like see what we can play around with a little bit. We're going to mess around with the code, and then we're going to wrap this up here, and I want to read the rest of this because it's going to say that we can change our tokenizer. Instead of creating a full dictionary tokenizer, which is what we did. That's what I did. I didn't even follow the tutorial. I just went for it. I'm like, I know what we need here. We need a dictionary tokenizer. Apparently, if we updated that to take word stems, instead, we could have an even better LSTM. Level representation, do an LSTM over characters of a word. Let CW be the final hidden state. CW be the final hidden state of the LSTM. Really? So this is like an extra task that we got to do, and they're not going to tell us how to do it. I was going to do it a little bit differently. There are going to be 2 LSTMs in your new model. The original one that outputs positional tag scores, or POS tag source, and the new one that outputs character level representations of each word. To do a sequence model over characters, you will have to embed characters. Yeah, that's what I thought. The character embedding will be the input to the LSTM. So how are there 2 LSTMs? Are there 2 layers? How would that work? Hey, Mark Lemon, welcome on in. Thank you for clicking the hi button. You have 2 separate LSTMs. 2 separate LSTMs? You mean two completely different models? Word can take a word embedding and a character embedding. Do you have two LSTM layers, is what you're saying? Wayback Machine has the first website ever to be archived on it. Is it? Does it, or did it archive itself? Or it has the first website ever? Yeah, and they feed each other. Yes, two layers. Okay, got it. So if I go up here, so we're basically going to have an LSTM2, right? Or a LSTM letter and an LSTM word, something like that. Is that what that's going to be like? I mean, it'll be obviously got to change the sequences here, right? So it'll be hidden dims like this, something like that. So what does LSTM take as input? Right now it takes tokens, right? So we got a dictionary here. I'll show you. Do we save it? LSTM dictionary. Here you go. So here's the inputs and here's our tokens, right there. Inputs and tokens right there. So it gives it a bunch of numbers. I tried to one-hot it. It didn't like it. It didn't like it. Obviously, it wants tokens. It wants tokens. It becomes somewhat obvious that it should work. Oh, like draw the input and output shapes. Oh, right. Let's see here. And that's naturally composable. So yeah, shape is TX. So today we are going to be learning our LSTM. We're going to run through this extra task here. Instead of using word embeddings, we're going to use letter or character level embeddings. And we're going to tokenize our input per character. And we're going to see what the loss is. We're going to see what that looks like. That's the plan for today. Like there's also a batch, but in omitting it for brevity. I tried to do the batch. I actually got the batch working. However, I was unable to get the negative log likelihood loss to work with a batch. I was failing at getting it to work with the batch. I tried and it was like, nah. You want to do that? You can't do that. Nope. No negative likelihood loss for you. In a batch format, probably because we were batching it as, words. And so it could only have so many dimensions. When I tried to add a batch dimension, it just wouldn't go. It wouldn't go. Thank you for the hearts, you guys. Oh, you had the shape wrong. Yes. Okay, so negative likelihood log is the way. Yeah, that's what we were doing right now. That's what we're doing. So you think you make the model do a collapse so it has no time for the prediction. That also works. We were messing around with that. We were doing all sorts of things with our output here. All sorts of things. So many different things we were trying to do. All right. So let's see if we can reduce our loss. That's what I want to try. Let's mess around with this for a bit. Let's do 600. This is 100% CPU. Okay. Let's do 1,000. Let's reduce the learning rate. Okay. It's actually not nearly as much as it needed to be. 5. Okay. Simple a mean on dimension 1 would work too. I suppose we could have done that. That makes sense. We could have done that too. Does this really need to be 1? Okay, see 1 is just a smidge too big, so let's do 0.7. So we've got our mask, and then we need to sample over our data, and then we need to sample over our words, and we're going to sample over our characters. Or, how about this? We don't need to enumerate it, right? We can do something different. Oh, do we even need to? Wait, hold on. Where are we at here? For if word and dictionary continue, or if letter and dictionary continue. Are we even using index? We're not. So we don't even need to use index anymore. So we can just say this for word in, like that. There we go. You're uploading to YouTube? Nice. Nashville was great. Nashville? Is that like a TV show? That's also a place. It's a location. Did you go to Nashville? So we got word, and then we're gonna go character. We're gonna go we'll just say char in word. word dot split. And I think we can do that. Python, we'll say hello, and I think we can say dot split. No, we have to say split on nothing. Empty separator. Yeah, it is empty. How do we split? Oh, we just do list. We do list. I think we do this right. List. E please, E. Yep, E. Thank you. I think we need to. It's getting a little bit much here because we have to do one extra level. Dictionary, sentence, for word, and can we do an extra for? So we say for word. So for char in word. Can we do that? Something like that, right? And we don't need about word length. Word less than the split. Oh, right. Because the sentence is fine, but it's not going to be split. It's going to be list. This is a whole different thing. It needs to be this length, the full length of the sentence. So I guess we could just do lang. We don't need to list it. There's no point to list. We get the whole sentence, which is every single character. And then we need the word. It's not the word. This is the padding. So we have to deal with the padding here. You know, do we though? Because what is the full total embed size? It's gonna be based on the length of the sentence, of the max sentence. Max sentence length is here. Okay. Got it. Okay, so we need to do list, no, length of the string. So we don't need to do this. We need to do length of X. There we go. There we go. So that'll fix that. We're going to have to break a whole bunch of things in order to get this character level thing to work. We're going to have to really mess all of this up, aren't we? We're going to mess this up so much in order to get this to work. Okay, so we're going to need to print out our features. So we're going to max sentence. Here, dictionary. We need to get the letter. We just need to get the letter code. We need to get the letter code is what we need to do. This dictionary comprehension is getting a little too much. Just a smidgen much. Just a little bit. It just needs to be an array, a simple array. So I think we can do something like append. Let's simplify this. All right, for word. No, we don't even need to do word anymore. We don't. We don't even need to do word. What am I doing? What am I even doing? Index word. No, we don't need to do this. All we need to do is character. Char. Oh wait, that's the wrong one. That's the wrong one. We gotta do this one here. Okay. This. Here we go. Right? Wait, let me read that again. Sample 0. Right. Too lower. Okay. We need to grab this here. There we go. For char in sentence. There we go. There we go. Much simpler now. Sample 0 lower. We already have it here. And that's the chars. We gotta put list. We gotta list it. List. For char in. There we go. We're gonna say features append. Where are we doing this at? We're doing this at right around here. So we need to put in a mask. We need to put a mask in. Oh wait, let's do range. Okay, so we need to go about this a little bit differently. Okay, that's right. Okay, so we need to loop over this as the top level. For features. Wait. Oh, darn it. Okay, so no, we have to do feature. So we're gonna call this feature. Say feature. Feature equals. Okay. Where are we here? Features. All right. So we're gonna, and at the end we need to say features dot append feature. Okay. Sample data features. It's going to be the maximum length. It's not a max length of the sentence. I mean, actually, technically, yes. It's the letter length. So that gets us the full input size because it needs to be consistent. And then we need to mask anything that does, or pad it. We got to pad, right? We got to do some padding. Anything that doesn't match from our vector, and that would be a pad, which is going to be the mask here, right? So we need to figure out if that's going to be the mask or not. Difference between programming and software engineering. Then we need to say, not features, we need to say feature. So that gets us the full range. Wait. It's already a range. We don't need to do enumerate. Okay. So there's our index, and we're going to say feature index equals and then we need to get our sentence here. So we got our sample. So let's grab our sentence, or chars. We'll say chars equals this. There we go. And then we need to loop through it. We need to loop through it and create a feature list here. And then we need to append it. So that way we got our full data set after we vectorize it. Okay. Sounds good to me. The feature index here. All right, so we got our features, we got our characters, and then we need to do something here. Right here. Okay, so if the length, all right, so length length equals max sentence. We need this right here. The length of chars. So if index, let me see here, word, so it's basically this right here. So if index less than the current position. So we've got my characters, I got my length of my characters, which is the length of the sentence. I've got my features, which is going to be the full range of the maximum sentence for the max input size. We need to loop over all of them, and we need to see what our current position is bigger than the length. Is this the right way? So is index bigger than length? And then we need an else. So if the index position is beyond the length, then we need to add the mask here. Otherwise, we need to append the token, which will be the, how do we get the token now? We need to say index of the sentence. Where is that at? Data sample. The chars, here we go. Like that, okay. I think we did it. I think that's the answer. All right, let's see if we can print this out. So char index out of range. Chars. So my chars, yes, it is going to be out of, okay. Here we go. Sample 0 lower list chars, print chars. Let's see what we got here. Okay. Our chars is, yep, that looks correct to me. Okay. So the dog ate the apple. Good. All right. Okay. that's the correct number of chars. We're going to get the length. Let's continue onward. Also, wait. No. Yes. We do have to do 0. Okay, we do have to do 0. So that gets us the chars. Because the others are the tags, right? You got your sentence and you got your tags. Length, chars, features, index. And then where's the error at next? On line 58. Good, right there. We're already on it. We're on it. So here's our chars and then the index. So we need to flip these. Yep. Done. Done, you guys. Easy. Oh, we need to do it with the labels too, don't we? Well, do we though? Yeah, we do. I don't even know what the labels. No, Dana, what are gonna be? What do they need to be? Do they need that? No. So this needs to be a different. So that's the max length of that. I need it to be the words. So we need to do it on the words, not on, because this is the outputs. So there's too many classes here. So we have to reduce this to the words themselves. To the words themselves. And the max sentence is going to be a different. So we need to say max word count and max letter count, which are two separate things. All right, so max sentence length is going to be okay. And so we're going to say, instead of max words, we're going to say something else. We're going to say, this is going to be called max characters. Max characters. Let's update that now. This is going to be here. And not there. This will be max words. All right, so I need my max words is going to change. That is going to be a little bit different. We need it not to be the length. However, we want it to be the number of words. So we can say dot split like that. That'll give us the max words. There we go. That's what I'm looking for. Right there. Let it crash and then we'll run into it here so we can see. Okay, so we got a 29 by 4 because there's 29 letters. Right. Okay. That's going to be the output of it. And our target size is only 7. Okay. So I need to think about that for a second. If that's the case, we don't want to classify every letter. We want to classify the number of words. We do gotta wrap up here, you guys. I think the plan for tomorrow is to figure out how to update the criterion. Well, we don't even have to do that. I think what we need to do is update it so the output of the LSTM is giving us. Can we do that though? Because the number of inputs that we're sending into it is. So how do we even do that? How do we combine the two? I don't even know. This is something that I'm not sure about. If we want to classify the words rather than, I know we can classify the letters. We could totally classify the letters, but there's no point to it. Steven, you want to pool it? Oh, okay, yes. All right, let's do the pool. Okay. Neva, thank you. I was like, why is it not working? So we need to pool it, which we do up here. So we're gonna say our pool. All right, I'm gonna try the embedding. So embedding, and this will be let's see here. Embedding dimensions. What is that supposed to be again? Oh, it's just here. Okay. Why 12? Oh, is that going to be the output? I forgot. Is this the sequence length? No, because we've got our dictionary length and tags length. And then our what was it here? 1 second. Let's see if I got it right. Here we go. Embedding dim. What does embedding dim equal? 6? Huh. Let's say what our embedding output dimensions are going to be. So our, let's see here. It needs to be the length. It's got to be the same thing, right? So we have 2 embeddings. Vocab size, which we have there. And then we need a word vocab size. And it's going to give us embeddings there. Okay. I think I have a general picture. So I see what we could potentially do here. We need based on what it's giving us here in our hint, which is what we're gonna have to do tomorrow. I think this will be the plan for tomorrow. We're gonna try to get this exercise to work. Is to finish this exercise where we're gonna get our word level LSTM into a character level LSTM. It seems like it'll work. I mean, we got it to train with words. Why can't we get it to train with letters? And keep the same classifications on the words. Oh, by the way, Steven, if you need help with this later, let me know. We might need it. We might need it. That might be the plan. So we do have some problems here that we will need your help with. It might happen. It might happen. We've got a generally good idea of where to go, though. So I need to create 2 embeddings and 2 LSTMs, which I have here. And then we need to take that other embedding and then put it in the middle. We'll put it right here. The other embedding needs to go here. This will be like word embedding. And this will be the letter embedding. We need to switch those up. So that's the plan. That's the plan for tomorrow, you guys. Had a lot of fun today. See you guys tomorrow. I'm going to play around with making my laptop's boot sequence fancier. Oh, Jinlu, sounds good. The GitHub. We could do that. All right, let's do that. All right. It's going to be broken, though. It's going to be broken. Git. All right, git commit dash m. We started char level. It is broken. There you go. We pushed the main branch and it's broken. There you guys go. Nice. You're gonna do a PR